So welcome to the last lesson of our chapter. And sorry I didn't post last night's video last night, but I'll post it today. Okay guys, don't shout out your answer, but look at the word non-linear. Think about that word for 10 seconds. Non-linear, think about that, don't shout out anything. And I have one more apology. I want to apologize for not titling my worksheets well this chapter. All my worksheets have pretty much the same title. That was very confusing. Hopefully you figured it out. Okay, so what does nonlinear mean? What does nonlinear mean? Not a line, right? Why would we study nonlinear systems? Have we been studying linear systems or something? Yes, we have. We've been studying linear systems. Let's talk about what that means. So we're talking about nonlinear today because we've been talking all this time about linear. Okay? Everybody look at the board. Thank you. Oh, that's not what I meant to draw. Let's get a real pen. Okay. We've been talking about two-dimensional linear systems where your equations look like ax plus by equals c and dx plus ey equals f or something. And what's going on is you have two lines, right? Either the lines cross or they don't cross, or they're actually the same line in disguise. Right? Okay. Then we did a 3D linear system, but still linear. So the 3D linear systems we spent quite a few days on. The 3D linear systems have equations like ax plus by plus cz equals d, ex plus fy plus gz equals h. But they are planes, and we need three of them if we're going to find contact. So it goes on, ix plus jy plus kz equals L, right? Three equations, three unknowns. They are not lines, but they are linear equations, which really just means there's no x squareds, no y squareds anywhere. That's actually what linear means. It doesn't necessarily mean straight line. So please erase the idea that from your mind that linear means line. It really means more degree 1. Or even degree 0 is considered linear. Okay? In a lot of ways. So like a horizontal line has no x at all. But it's still a line. Okay, so these are not lines, they're what? These are planes in space, right? What were you going to say, Jack?
I was going to ask, what if they were all degree 2?
That's what we're going to talk about today.
Oh, okay.
Yeah, those are those are like conics systems. Like if you have two hyperbolas and we're going to try and see where they cross. That's exactly what we're doing today. But you're like 2 steps ahead of me. I was going to ask you what you thought nonlinear might mean next. Okay? So this was like 3 straight and flat planes. 3 straight planes. Linear means straight, you could say, I guess. They might cross. They might not. In this picture, are they crossing? No intersection. How about in this picture? Are the 3 planes crossing? They are. They form a line. This is supposed to look kind of like a book. Okay? This is the front cover maybe, and this is the back cover. There's a page sticking out of it. Okay, so this is kind of like a no solution case. This is kind of like an infinitely many solution case. Or we even have the one solution case, which is kind of hard for me to draw. I'll try. You have a plane. You have another plane that intersects it. Like that. and then a third plane comes along and cuts through it at such an angle as to intersect this red line. So where's the third plane? Well, it could be in a number of places, but how about just like this? So I'm not an artist, never claimed to be an artist here. Some of this stuff should be invisible, like that should go away. Let's see, that should be invisible. And there'd be another line here. Not too bad. The point is you have three crossing planes, and the point of contact is here in green. I know, you're probably thinking, Mr. Short can't draw, and he should have added something or not added something, or I don't know. Oh, I know what I added that I shouldn't have. I should not have had this little part. Is that right? Oh, man. Okay. Have fun drawing. Okay, those are fun to draw. But my point is not to have an art class here. We have one solution here. And most of the problems you've solved have had a single solution. -1, 4, 3. It's a place in space. But the systems are linear because everything's flat, and there's one solution in our solution system. Yes?
Oh, wait, for an equation like that, could you be asked, like, how many times does plane A intersect plane B? Because that's one line. Each plane intersects another plane with one line.
That's right.
But they intersect together at one point.
That's right. That's why you need 3 of them to determine a real point of intersection. Planes are two-dimensional, but they're in 3D space, right? And then when you have one plane is defined by 3 points, and we have 3 planes, it defines 1 point. It's true. Most of the time. Okay, but these first 2 cases are actually kind of rare. Okay? And there are other cases too. We had other pictures. If you remember, I put up like 5 or 6 pictures. But all of them are either no solution or infinitely many solutions, or I think this is the only picture we could draw with one solution, although you could tilt the planes a little bit. They don't have to be perpendicular. All right, but let's go on now and ask, what do you suppose nonlinear means? Okay, should we expect straight shapes? Probably not, right? Both a line and a plane are flat. Lines are flat, planes are flat. Right? So we're not dealing with that anymore. We're nonlinear. Also, we would not expect our equations to be as simple. Things that are not straight have x squareds in them, right? Y squareds, that sort of thing. Okay, so here is our objective. A nonlinear system basically would be a set of equations that represent like ellipse and parabola. Okay? These are nonlinear equations. Ellipse, parabola, not straight, right? What happens when you put one on top of the other? Well, a number of things can happen. If your parabola is not centered at the origin, it could be that you have no contact. Okay? So we're trying to put these together into one meaningful picture. It's possible to have a drawing where we have a parabola and an ellipse, and they just simply don't touch. That could happen. We could have a parabola and ellipse, and they might touch once. Or you could have a parabola and an ellipse that touch twice. Can you draw me a picture where they touch 3 times, please? And when you're done with that, can you draw me a picture of them touching 4 times? Or maybe 5 times? See if you can get them to touch 3 times, 4 times, and even 5 times. Okay, so it's not very hard to make them touch 3 times, right? Just move your parabola down a little more. 1, 2, 3. Raise your hand if you have a picture of something like this. Okay. All right. 4 times. Anyone get that to work? Anyone able to draw it so it touched 4 times? Okay. Maybe something like this. Was anyone able to get 5 solution points? Is that possible?
Could the line slope like intersects and then runs tangent the parabola too?
Okay. So it turns out that 4 is the maximum. Okay? We'll prove that. We'll see not a formal proof, but that will emerge from the mathematics. As we try our hardest to solve these problems, we'll see that it actually is not possible to get more than 4. But it is possible to get 0 or 1 or 2 or 3 or 4 possible answers. Now, second period, I had a student who drew this picture. Where there was an infinite number of contact points in here. What's wrong with this picture? This is a tough question. This is not actually possible. But it does seem to defy what I said a minute ago. I said a minute ago 4 is the most you can have. This student just drew a picture of an infinite solution case. Or did they? This is a tough one.
The slope is always changing, right, of the ellipse. So for a parabola to follow the exact slope the whole way, the equation would have to be constantly changing an infinite amount of times. An infinite amount of times.
Okay. Any other comments?
Not to mention an ellipse has an x squared and a y squared, when parabola only has one of the 2 variables squared. And the 2 shapes have a different eccentricity no matter what, at all times.
Okay.
Eccentricity.
Different eccentricities?
What do you?
That's okay. I've heard people say it both ways.
Go.
Okay, so this is actually a really good question, because it does seem to defy what I said a minute ago. But in this picture, either that parabola is not a parabola, or if that parabola is a true parabola, then that ellipse is not a true ellipse. Let's just assume that that green thing is a perfect parabola. Okay? That means that this purple thing could not be an ellipse. Here's why. The bottom half of an ellipse cannot be parabolic in its shape. It cannot have the curve of a parabola. Okay, it's impossible. So, actually, both of what Jack said and what Matt said are true. If you try to construct an ellipse whose bottom half is the equation of a parabola, it will have to have either x squared or y squared. It can't have both. And since it's not an ellipse unless it has both, an ellipse can never be truly parabolic in its shape. And then what Jack said is true too. What looks like contact in here really is not contact. If you zoomed in closely, you would see that the purple and the green actually don't touch at all, except maybe at the vertex. So if you zoom way in, really, really close, you would see this way up close. One contact point. Okay, so your eyes are fooling you on this. This is not a valid case. Either that parabola is not a real parabola, if the ellipse is a true ellipse, or vice versa. Okay.
Parabola near the shape of the circle?
No, the same issue. The circle's in the ellipse family, so it has x squared and y squared. In order to force it to look just like a parabola, it would have to lose one of those 2. Yeah, those are pretty strong arguments. It's not a formal proof, but it's a strong argument, right? Okay, so let's go now to some examples, problems we'll see today. So let's go ahead and go through some examples here. If you see solve the nonlinear system, what it's saying is find the points of intersection. So don't be intimidated by this. It just means find the intersection point or points. That's all it means. And so let's say that you're dealing with this case. 3x minus y equals negative 2. 2x squared minus y is 0. What is going on here? Well, if you isolate y in this first equation, you get y equals 3x plus 2. And if you isolate y in the second equation, you get y equals 2x squared. So this particular problem, it wouldn't be very hard to graph it, just to kind of see what's going on. What is going on here? Well, you have basically a parabola and a line, right? The line looks like this. This is your line. Okay. This has the equation y equals 3x plus 2. Nice steep line passing through y equals 2. And then we have this parabola, 2x squared. You know, it's a little bit vertically stretched compared to just x squared. See? But see how they touch twice? Our goal is to find those two crossing points. Find the crossing points. Now you could probably graph this one and get them right, but we don't trust our eyes or our art skills, right? So we would probably want to use like one of our algebraic methods to solve this. I suggest you not use matrices, okay? Because matrices are kind of designed for linear type things, like lines or planes. There are a very, very small set of problems you could use matrices for. I do not recommend matrices. Let's just use elimination or substitution for everything today. Eliminate or substitute. Since I've already done the hard work of getting y by itself both times for both equations, why not just set these two equal? Right? They're both equal to y, so let's set them equal to each other. We'll force their y coordinates to be the same. Okay, let's see. Where would these have the same y coordinates? Okay, so we'll take 2x squared equals 3x plus 2. And you need to know how to solve that, of course. Just bring everything to one side. Factor it. And you get x equals negative half. X equals 2. So which is it? It's both. See the two green points? These represent those two green points in the picture up above. Okay, so now we need the y coordinates, of course. So we're going to plug those back in. How about we just plug them into the y equals 2x squared equation. So let's start by plugging in the negative half. I just plugged in negative half, and I got half. You can follow my work there. Okay? When I plugged in negative half, I got half, which means that the graph passes through negative 1 half, comma, half. I'll bet that's the green point on the left. Okay? If I let x equal 2, which is also a perfectly valid solution, and I plug that into 2x squared, I simply get 8. In other words, 2/8 is also a valid solution. I expected two answers on this problem anyway. Here they are. Okay, so what we just found was the intersection between a line and a parabola. By the way, could a line and a parabola touch 4 times? No, because the line is linear. So you can predict, actually, this is kind of how you can do it. If both equations have an x squared and a y squared, when you're starting, then those can have 4 solutions. But if one of them is a straight line, then the most you could ever get is 2. And if they're both straight lines, the most you could ever get is 1. Unless they're the same line. Okay, let's go to the next example. So you can kind of see what we're doing now today, right? Example 2, I picked this problem. X squared plus y squared equals 13. x squared minus y equals 7. Now in this problem, this one is a circle. This one is a line. No, it isn't. It's a, what is it? Parabola. Yeah, because it has the x squared but not the y squared look, right? Okay, you can actually do this one by graphing too. It's actually not very hard to see that it has, 2 solutions or 4 solutions or whatever. But most people don't graph these. You spend all this time graphing, and the best you get is sort of a rough idea of what it looks like. Why not just solve it? I see a chance to subtract my equations right now. So there's no one way that's better, you guys. This time I thought I might subtract the equations. Last time I did substitution, setting them equal, that's considered substitution. Here I'm just subtracting them. Why did I subtract them? What's the advantage to that? Yeah, it does something for me. It actually gets rid of x squared. Good riddance. Okay, so this gives me 2y, no it doesn't. It gives me y squared minus y, because I can't really combine these two well, can I? Oh, and it's plus y. Why is it plus y? Subtracting a negative y. Good. And then I have 13 minus 7 on the right. Okay, there's your equation that survived the subtraction. And it does have one variable. That's nice. Let's solve it. So let's bring everything to one side and factor. Oh, it looks like we got y first this time. That's fine. Looks like y is negative 3 and y equals 2. They're valid solutions. Okay, let's pursue those thoughts. If y equals negative 3, and our equation up above was x squared minus y equals 7, we could plug this in right here. So it's basically x squared plus 3 equals 7. In other words, x squared is 4. And yes, x is plus or minus 2. Interesting that we got 2 answers there. We'll come back to that in a minute. Okay, now let's look at if y equals 2, what happens? Well, x squared minus y was 7, remember. So you can substitute this in right here. So you get x squared minus 2 equals 7, and x squared is 9. So this time we get that x is plus or minus 3. Why are we getting so many answers? Let's see what all this means. When I plugged in y equals negative 3, I got 2 x's, right? So what that means is, whether x is 2 or negative 2, it doesn't matter. Either way, y is negative 3. See? I used one y and I ended up with 2 different x's. So I've got the same y here, but 2 different x's. Obviously, this is not a function. Right? Well, actually, these are not graphs. We're not graphing. We're just looking for intersection. And besides, they have this different x's. Never mind what I said there. But let's take a look at the second one. The second one is saying that when y was 2, we got 2 x's. See? All right. So anyway, this is just saying that when x is 3, y is 2. When x is negative 3, y is 2. So how many answers did we end up with altogether? 4. Here are the answers to the problem down here. Now, if you took the time to graph here, you would see it really does touch 4 times. Okay? I'll draw a rough sketch for you. Basically, you have a circle like this, and it's centered perfectly at the origin. And then you have a parabola that comes up from underneath like this. And what you're looking at are 4 points, 1 in each quadrant. Obviously, this would be the point 3, 2. This would be the point negative 3, 2. This would be the point negative 2, negative 3. And this would be the point 2, negative 3. And that's just the way it looks in the end. But you can't really estimate by graphing, right? Okay, so that time I did sort of a subtract, which is like elimination. Okay, let's go on to the next one. Picture is sort of optional. It's just cool to look at. Can I go to the next page? All right. Okay, so for example 3, I tried to mess with you and I messed up the equations for you. Oh, yuck. So what has Mr. Short done to ruin your life here? What did I do to ruin your life? A couple things. Divided by x. What's that? Yeah, this is not general form or standard form, the second one. The first one's in the form called general form, but that second one is all messed up. Can we fix that second one? Multiply by x to clear the fractions? Okay. Let's do what he suggested. He suggested we just multiply by x on every term. Okay, that's going to give me an x squared here and an x here. We're going to lose that fractional look for this y squared minus y over x. The x is going to go away. The right side is still 0. Is that even legal? Can we do that? Are we allowed to multiply it by a variable like that? Okay, there's two things about this you have to know. One is the principle the principle in algebra that allows us to multiply both sides by a number. There is one exception to it. You're not allowed to multiply both sides of the equation by what? 0. And technically, since we don't know what x was, we could have just multiplied by 0. But then, right? Okay, so what are we going to say?
It can't be 0 because x is the denominator.
Okay, so there's kind of two things going on. One, we multiplied by x, right? But we're assuming x isn't 0. First of all, we wouldn't be allowed to multiply by the green x if it's 0. Okay, not allowed to, period. Second, x isn't 0 anyway because the denominator here is x. So we're not allowed to use x equals 0 for that reason either. So I guess what we're saying here is go ahead and do it, but make a mental note now that if x equals 0 ever shows up later in this problem, it needs to be thrown in the trash can. Okay, because it is going to pop up later. X equals 0 is going to pop up, but it is a phony, a fake, an imposter, and we're going to toss it out. But we're making that decision right now. Okay? So let's make a little mental note or jot down on the side. X equals 0 is not a valid solution. Okay? If you don't write it down now, you might be tempted to keep it in the end. Let's go on with the problem now. Our system looks a little better. Okay, so you guys were able to decipher my system. And it looks like this now. I'm going to distribute that negative right there. Oh, this isn't so scary after all. Especially if you subtract the equations. Right? So I'm going to subtract these equations. Oh, lots of stuff drops out here. Okay, so what cancels out? The x squared's gone, right? The x's. Does the y squared cancel out? No, we get 2 y squareds. How many y's do I have?
2 y's.
No? Remember, you're subtracting, right? You're subtracting out front, so be careful there. Yeah, it's supposed to be a negative 4y right there. The right side 0. Oh, and I forgot the little 2 that had no partner there. Okay, so obviously this needs to be solved. Question?
In the original problem, wasn't it y squared, negative y squared minus y?
Yeah, but the y squared minus y was on top, right here. This is on top, so it deserves its own parentheses. When you multiply by x, it comes out as y squared minus y in parentheses. Technically a fraction bar, I mean. This is something that they don't really tell you in Algebra 1 very clearly. Listen very carefully. This fraction bar serves the same thing as, serves the same purpose as a parentheses. It's one of the grouping symbols. You know, you learn parentheses and brackets, and you learn, you know, the curly brackets and all these things for organizing your work. Well, the fraction bar is a grouping symbol. I just don't know how clear that comes across in Algebra 1.
Oh, so you have like.
So the parentheses are very important. Once you lose the fraction bar, you have to replace it with a different grouping symbol, namely parentheses. Yeah, very important. Okay, so I didn't make any mistakes there. But we need to solve this, so why don't we divide by 2 real quick? I just divide by 2. And we end up with y squared minus 2y plus 1. This is just y minus 1 times y minus 1. So y equals 1 is like a double root or something. Maybe a touch point? Like a point of tangency or something? Remember, double root means the graph touches the x-axis. This probably just means the shapes brush up against each other or something. That's a good logic jump. But let's go on. If y is 1 only, let's go on with the problem. If y equals 1, remember in the beginning, x squared plus x plus y squared minus y, or minus 3y plus 2 equals 0. Let's plug this into there. That's awful, but this was one of our equations from earlier. We can plug in 1 here. You have to do it for both y's. But you get x squared plus x plus 1 squared minus 3 times 1 plus 2 equals 0. This just all cancels out. Bam, bam, bam. X squared plus x equals 0 means what? X is, factoring, we get what? X is 0, x is negative 1. But we said what earlier? If we ever see x equals 0, we're going to do what? No, we're going to put them in the trash can. You weren't listening. So draw a trash can. Label it basura. Did I say it right? Nice. That is Spanish for trash. Thank you. Trash. Throw it away. We're just going to keep this answer. X is negative 1 when y is 1. Okay, now the graphs on this are very interesting. If you actually graph these two, you'll see that they look like they touch twice, but they don't. You guys ever seen those, that magic trick where the magician holds up the rings and links them together? I'm sure you've seen that. Magician has a bunch of rings, right? And the magician can link them together or pull them apart, right? It's kind of like that, except one of the links, of course, has a little tiny hole in it. You guys probably already knew that. Hope I didn't spoil anyone's surprise. There's a tiny little hole right in the, I'm exaggerating it, but there's a gap in the ring. So when the magician puts the rings together, it might look like they're touching or linked, you know? I mean, it might look like if the magician held it like this, it might look like they're touching twice, but they really aren't. So technically, the magician could hold the two rings like this. That's not a point of contact. That is a point of contact. That's kind of what's going on in this problem. Without getting too detailed, this is not actually two circles, but that's sort of the idea. So it looks like two contact points, but it's only one. That second contact had a hole in it. All right, let's go on. Some of you are like, well, that's how they do that magic trick. Okay. Example. We'll talk about magic shows later, guys. Yeah. One more example here. I actually have two more examples, so I'm going to have to pick which one I'm going to do here. Let's do this one. Okay. So in this particular problem, I'm not too sure what that first shape is. I think it's a parabola, but you see that xy term? That guy has a way of messing up everything. All right? 3xy, what that does is that takes our conic and it tilts it. it tilts it. So you studied so hard to figure out which ellipses are horizontal and which ones are vertical. Well, if there's an XY in the problem, it actually twists it anyway, so it messes up everything. And if I had another day, I would teach you how to deal with that XY term, determine what kind of conic it is, even get rid of it.
You
How to
had,
get rid of
you
it.
had a sub here when you were sick that one day, and he was talking to us like the whole day about that. Like,
Yeah,
if there
I just
was
don't have time to teach it. It's very, very tedious to do. But one thing I can do is solve the system. Even if I don't know what shape it is, I can still find the intersection points. So I'm going to multiply this by 2, and this gives me 6xy minus 4y squared equals negative 4. And if you line that up with the original second equation, these do add together quite well. And you get this. Okay, now you might say, Mr. Shore, you did not accomplish anything. You did not get rid of y squared. I mean, you did not get rid of y or x. I didn't. You're right. I formed a linear combination that I think is easier to work with than these original equations. Especially that first one was horrible. So what I'm going to do now is I'm going to solve this problem as though this was my system. I'm using the original second equation, which I was never scared of, and I'm using the linear combination of equations 1 and 2. I'm going to solve this as though this was the original problem. Okay, so how am I going to solve it? I'm going to isolate the y in this equation here by subtracting the 9x squared to the other side and dividing by 6x. Can't see it? What can you not see? Okay, I subtracted the 9x squared over and divided by 6x. This gets y by itself. And then this thing becomes a nice replacement for this y right here. So the blue will go in for the blue there. Let's give it a try. Actually, I changed my mind. I think I will put the blue in. I'll put this blue object in right here. Yeah, I have a couple options. I think I would rather do that. It is complicated, but it's solvable, and we will get it done here. So we have this 9x squared plus 4y squared equals 10, and we're switching out that y with this garbage. So this is that blue thing inserted. Okay, before you freak out, this does produce a 4th degree equation in x, but it factors. It solves really easily. So I'll try to finish it up here before the bell rings. If not, we'll just catch it on the video. But it comes out to 9x squared plus, and if you don't mind, I'm just going to reduce the inside of this a little bit. I'm going to change this to a 2, a 3, and a 3. I don't like the 6, 9, 6 look, so I'm changing it to 2, 3, and 2, 3, 2. Yeah, 2, 3, 2. Oops. 2, 3, and 2. Okay? So I'll write it one more time before I square it. Okay, so it's going to be 9x squared plus 4 times, and the top is 4 minus 12x plus 9x to the 4th. The bottom is 4x to the 4th.
Wait a second, it's 12x squared.
12x squared, thank you. Then the 4's cancel out. And the bottom is x squared, not x to the 4th. Sorry. There we go. But the 4's cross out. And then let's multiply by x squared throughout the equation. And remember, x cannot be 0 now. So x cannot be 0 if we do that. So let's go ahead and finish it up. This is 9x to the 4th plus 4 minus 12x squared plus 9x to the 4th equals 10x squared. In other words, 18x to the 4th minus 22x squared plus 4 is 0. I brought everything to one side. Okay, and then this actually can solve pretty easily. You guys know the quadratic formula? You could just use that if you want. Just go x squared equals negative b plus or minus square root of b squared minus 4ac all over 2a. And unfortunately, this is just 49 in here, so it's just 7. So you end up with x squared equals 18 over 18, and x squared equals 4 over 18, or you could say 2/9.
Please report to the attendance office. Ellie Wilson, Jordan Wilson, Amanda Lake, please report to the attendance office. Ellie
These need to be
Wilson,
plugged in to get the
Jordan
y's,
Wilson, Amanda Lake,
but
the attendance
I'll do that on the video. Have a good weekend. You'll get a worksheet.
I have a question on one.
Okay, so we just got our 4 values of x. Now it's time to go back and get our y's. And let's take a look at what equation might be best. So if you kind of go up, you can see the y right here. This guy here, this guy is a good choice. That will help us down below. So let's take that down here. There it is. This is what we had earlier, so let's go ahead and put in our x's here. So let's start with x equals 1, I guess. So y would be 6 minus 9 over 6. In other words, negative 1/2. Now let's do x equals negative 1, and we get 6 minus 9 over negative 6, so this is positive half. And now let's plug in root 2 over 3, and that gives me y equals 6 minus 9 times 4/9 over 6 times root 2 over 3. I meant to say 2/9, not 4/9, so I'll fix that in red. Right there, that's at 2/9. And this gives me basically 4 over 2 root 2, in other words 2 over root 2, 2 over root 2, I'll write that down here. In other words, just plain root 2. Okay, and then our last one, let me move this all over a bit. Our last thing to plug in is x equals negative 2 root 3. So y is 6 minus 9 times 2/9 over 6 times negative root 2 over 3. And this all comes out to be 4 over negative 2 root 2. In other words, y is negative root 2. Okay, so let me highlight our answers. So our answers are 1, negative half, negative 1, positive half, root 2 over 3, rad 2, negative root 3 over 2 over 3, negative root 2. And we can write our final answers down here at the bottom in blue. 1, negative half, negative 1, half, root 2 over 3, root 2, and negative root 2 over 3, negative root 2. 4 intersection points for our 2 conics. And remember, our first conic, we never even really figured out what shape it was, but we're saying it doesn't matter if you know the shape. If you know the method, you can find the intersections. All right, so there's your answer. Kind of neat. Okay, so one last thing I wanted to say that I didn't get a chance to say in class, and that is sometimes you get a no solution case, and I just want to show you what that would look like. Okay, so take a look at this problem. Let's say you have x squared minus y squared equals 4, and you have y equals x squared. Probably the easiest thing to do here is since your y is x squared, you could replace this x squared with y. We're saying in this second line that y is x squared, so it shouldn't matter if we write x squared minus y squared equals 4, or simply y minus y squared equals 4. So we're giving permission to replace this with a y. Okay, this is a little hard to solve. You'd have to bring everything to one side, and you would have to isolate y. Looks like it won't factor, so we use quadratic formula. So y equals negative b, right? So plus 1 plus or minus square root of 1 minus 4 times 1 times negative 4. Oh, sorry, this should have been a plus 4 right there. All over 2 times 1. Okay, so what happens is you end up with plus or minus, or 1 plus or minus the square root of negative 15 all over 2. You can see that this is non-real, right? And so what this means is that there is no real solution for y, which implies you'll never be able to plug it in to get a real solution for x. So no real x's. In other words, there's no real contact points. So let's just put there is no solution to this problem. Okay, so what happened on this? Well, actually, it's much easier than it all looks. If you look at this original problem and you just graph it, you realize, wait a minute, this is simply x squared minus y squared equals 4, which is one of the simplest hyperbolas ever. Just write it as x squared over 4 minus y squared over 4 equals 1. So that's just like this. A is 2, B is 2. And then y equals x squared, you've got that graph memorized all along here. Y equals x squared, it's just this graph. Alright, some said you even memorized it in Algebra 2, so it's supposed to be nice and smooth at the bottom, not have a cuss. But you can certainly see that this graph does not intersect hyperbola. Now you might say, next time I think I'll just sketch it first. And then I'll say, oh, no solution. Well, you don't always know to do that. And I can't really accept the drawing as proof of no solution. You might say, I drew it, they don't look like they cross, therefore there's no solution. That's not a valid proof. I can't trust the drawing that well. I need to see your work over here on the right. Okay, so this is actually what I would expect you to do. Write something like that. And that's the end of